Alright friends, welcome back. In this video we're going to go ahead and move on to the next section of Chapter 1, which is 1.2, and we're going to talk about linear equations in one variable. Now, I know that linear equations in one variable has been something that you have likely seen in very many algebra classes that you've taken before semester college algebra here, but very, very important for what we're going to be doing later on, so it pays to take some time now and just kind of make sure that we know all the ins and outs of linear equations before moving on to some more challenging stuff. So, a linear equation in one variable, by definition, is an equation of this form right here. This is what we call the standard form of a linear equation, and a and b in this context are just real numbers, and obviously there wouldn't be any need to talk about this sort of equation if a was 0, because then that would just mean that this term would fall away and we would just be dealing with b equals 0, and the only value b could take on would be 0 itself since it's equal to 0. So, that's just a little bit of rambling. Let's move on. So, in this first example, just solve 3x minus 6. Very simply done, guys, right? Again, the only thing I want to remind you about is just your order of operations. We always want to undo any additions or subtractions that we see before moving on to multiplications and divisions. And so, just kind of adding 6 to both sides here. 0 plus 6 on the right-hand side is just going to be 6 itself. And then finally dividing both sides by 3. Really straightforward. We do that so that the 3 over 3 just turns into a big 1. And 1 times x is x. 6 divided by 3 is 2. And there we have our final answer for this equation. Okay? So nothing too difficult so far. Okay? So just linear equations in one variable, very simply done. Moving on here. Some other types of linear equations might require that we take a look at more than one thing here. And so on the left and the right-hand side, it just says solve 6 times the quantity x minus 1 plus 4 is equal to 3 times the quantity 7x plus 1. Pretty straightforward here. The first step would be to go ahead and, of course, apply some distributive property on both the left and the right-hand side, making sure that we distribute 6 to every term inside the parentheses there, and 3 in terms of every term inside there. Okay? So 6 times x is just going to be 6x. 6 times negative 1 is going to be negative 6, and then we have the plus 4, and that is going to be equal to 3 times 7 is 21x, plus 3 times 1 is 3. And then the next step here, of course, would be to signify that we do have some like terms to combine here on the left-hand side. That would be negative 6 plus 4. And so that would be 6x is going to be minus 2 is equal to 21x plus 3. And then just continuing to combine like terms, right? I always have a tendency to want to combine my variable terms first, but you can combine the constant terms first here. It does not matter. You can pick whatever order you would like to go ahead and do that with. So I'm going to go ahead and move the 6x over to the right-hand side. That, of course, is going to mean that this is going to become 0 right here, just leaving us with 0 minus 2 on the left-hand side, which is negative 2. And that is going to be 21 minus 6. That is going to give us, I believe, 15. So 15x plus 3. And then, of course, just solving this in the usual way now that this is in more of your standard form here. So subtracting 3 from both sides, minus 3, we're going to get negative 5 there on the left, and 15x on the right. Last step of this, of course, would be to go ahead and divide both sides by 15, since that is the number we're multiplying times x. And so x by itself is going to be negative 5 over 15, and that is a fraction that reduces down to 1/3. And so x is going to be equal to 1/3 is our only solution for this linear equation. Okay, so just kind of reminding you of some pretty standard steps that you might see in a introductory algebra course there. Okay, moving right along, this is going to be something that is going to be a common theme in this video, is we're going to have some fractions with denominators, of course, in our equations. And so having a nice way to deal with that is going to be very beneficial as we move on and see multiple examples with denominators. And so what we're going to do here is we're going to do a process called clearing the denominators, and that's going to involve that we multiply this entire equation times something. Okay, we're going to distribute it in here in a minute. And what we're going to multiply by is going to be whatever number it would be considered to be the common denominator between the denominators that we have existing here. Okay, and so because we have denominators of 3 and 2, one of common denominator that we would go with would be 6. Okay, and so we're going to distribute 6 to everything into this equation. So 6 times this first term, 6 times the second term, 6 times 17. And here's what that's going to do, right? This 6 right here is going to combine with these denominators to make some easier looking terms for us. So let's say we did 6 divided by 3. That would simply give us 2. So that first term is going to become 2x. If we then do 6 divided by 2, that's going to give us 3. And so we're going to say plus 3 times what we had there, which is going to be 5x. And, of course, we know that that's going to be plus 15x in the next line. We're going to set that equal to whatever 6 times 17 is. And so you could either do that mentally or by using a calculator. That is going to be 102. Okay, and so we're going to end up here with 2x plus 15x is equal to 102. We are going to have some like terms there. That's going to mean we're going to have 17x is equal to 102. And then just simply taking 102 divided by 17 will give us our solution here. And so dividing on both sides by 17, we can see here that x is simply going to be equal to 6. Okay? And so that's just a coincidence that that solution ends up being the exact same as the GCF or the common denominator that we would have here to multiply times everything. But again, that's going to be a common theme as we go from problem to problem and we see a bunch of denominators is we're going to multiply the entire equation by what the common denominator would be so that we clear the fraction in this way. It makes it nice and easy. Okay, same thing here. Okay, this is yet another example where we have some denominators, and so this one is called a proportion. It's a rational expression equals a rational expression. So you could totally solve this by cross multiplying, but again, kind of going in the same theme as what we just did in the last example, where we multiply this entire equation by what the common denominator would be. Okay, so the common denominator, I believe, would be just the denominator that we would get if we would multiply both of these linear expressions together. So let's go ahead and do that. Let's multiply everything times x minus 3, x plus 1. Okay, well, when we do that, when we distribute this to the term on the left-hand side, what we're going to end up seeing here is that the x minus 3 on bottom is going to cancel with the x minus 3 right here. And so what that's going to mean for us is that we have the 2 times the x plus 1 that's left over. And we're going to say that that's equal to, whenever we distribute the x minus 3, x plus 1 to the term on the right-hand side, we're going to see that this term down here cancels with this term right here, just leaving us with that x minus 3 there. So we're going to say the 3 that was on top times the x minus 3, which is left over. And you can see here that this gives us the same result as if we had just cross-multiplied. So I tell you what, if that's something that is easier for you to recognize here, then you can feel free to look at this as simply just cross-multiplying in this problem, and you would get this exact same line here. Okay, the next step, of course, would be to go ahead and take these values of 2 and 3 and distribute them into their respective binomials that we're multiplying times. And so that's going to give us here simply 2x plus 2 is equal to 3x minus 9. And then continuing to solve this in the usual way, maybe subtracting 2x from both sides, getting 2 is equal to x minus 9, and then adding 9 to both sides, you would get x is equal to 11 here in this problem. Okay, so again, linear equations, very simply done, just taking a look at a lot of the different ways they could be represented and finding solutions for those. Okay, yet another example here where we have some denominators. We're going to clear the fractions. So multiply this whole thing by what the common denominator would be, and here because they're both divided by x, we're just going to go ahead and multiply everything times x and distribute that in. So if we do x times this first term, 15 over x, that's just going to leave us with 15, clears that denominator. When we distribute x to the second term here, the minus 4, that's going to turn into negative 4x. That is going to be equal to, distribute the x to this 6 over x. That's going to leave us with 6. It will clear that denominator. And then finally distribute this x to that plus 3 there. We're going to have plus 3x. Okay? And so combining some like terms here, I'm not going to specifically show these. I'm just going to kind of talk through them. If I add 4x to both sides, it's going to give me 15 is equal to 6 plus 7x. Subtract 6 away from both sides. It's going to give you 11 is equal to 7x. And then divide both sides by 7. We get x is equal to 11 over 7, the fraction. Okay, so that will be the solution that we have here. Turns out that we can have fractional solutions, which are no problem. It just means we ended up with a fraction. Okay, another example here. So we have a bunch of denominators, and again, we want to employ that exact same strategy. We're going to multiply everything times the common denominator that we would need to combine all of these fractions together. And so that would be simply here x minus 1 times 3x plus 1. And when we distribute that to all the terms, remember that we have this canceling action, right? When we distribute this to the first term, we're going to have the x minus 1 cancel with the x minus 1 out here. And whenever we distribute to the other terms, we're going to have the 3x plus 1 canceling with the 3x plus 1 that's out there, okay? And so we'll just go ahead and write down the result of that here really quick. So that's going to be 4 times the quantity 3x plus 1 plus 6 times the quantity x minus 1 is equal to 15 times the quantity x minus 1, okay? So when we distribute that into all three terms, 1, 2, 3, we're going to see that one of those factors is going to cancel out with their respective denominators and leave the other factor, okay? Distributed property times, so that's going to be 12x plus 4 plus 6x minus 6 is equal to 15x minus 15. We have a bunch of like terms to combine there on the left-hand side, so that's 12x's plus 6x's. It's going to make 18x's. And then we have 4 minus 6. It's going to give us negative 2. And, of course, that's equal to the right-hand side, which really doesn't have a lot for us to combine there. Maybe let's subtract 15x from both sides. We're going to end up getting 3x minus 2 is equal to negative 15. Add 2 to both sides. We're going to get 3x is equal to negative 13. And divide both sides by 3, and we will see here that we end up here with another fraction answer. X is equal to negative 13 over 3. Okay? So that whole process of clearing the denominators is going to be an easy way that you can solve a lot of these equations with a lot of denominators in them. Yet again, right here, we have another example, and what you may notice is that we have something that is pretty familiar to us here. If you look at the denominator of that term on the right-hand side, that x squared minus 4, what you may notice is that this is the difference of two squares. Remember that we can always factor that into x minus 2 times x plus 2, and it turns out that that is going to be very reminiscent of the other denominators that we have in the problem here. So if we just multiply everything by x minus 2 times x plus 2, then the same action occurs where we're going to have the x minus 2 here canceling with the x minus 2 out there whenever we distribute that in. The x plus 2 here is going to cancel with the x plus 2 on the outside when we distribute that in. And it just turns out here that because we have x squared minus 4 here, that whole thing is going to cancel out with this whole thing when we distribute that in here in a minute. So let's just write out the result of that. So we're going to have 1 times the quantity x plus 2 is equal to 3 times the quantity x minus 2 minus 6x whenever we do that. And again, that turns this into a lot easier of an equation to solve. On the left-hand side, distribute that 1 in, or just say that 1 times that expression is just that expression. Distribute that 3 inside to both terms of the x minus 2 there, so that's going to give us 3x minus 6, and we're going to say minus 6x. Okay, combining some stuff here on the right-hand side, that's 3x's minus 6x's. It's going to give us negative 3x's, and that is going to be a minus 6, and then x plus 2 on the left-hand side. So maybe let's say we add 3x to both sides. It's going to give us 4x plus 2 is equal to negative 6. Subtract 2 from both sides. We're going to get 4x is equal to negative 8. And then finally divide both sides by 4, and we here get x is equal to negative 2. Again, sorry for kind of blazing through these, but again, these linear equations here really no need to really dwell on the subtle nuances from problem to problem here. If you guys need additional help with these, always feel free to come see me. We're just working out some examples, okay? Find intercepts algebraically, right? So again, whenever we graph these linear equations, we could use a graphing utility, count where it crosses the x and y axes respectively, and get our intercepts that way, but the problem is we don't always have a graphing utility. And we don't always have graph paper to create a nice picture for ourselves, so we need an algebraic way for being able to do this. And the way that we would want to do that is we would go ahead and plug in, say if we wanted an x-intercept, we would need to go ahead and set y equal to 0 and then continue to solve for x. Again, if you want the x-intercepts, you're going to set yourself up so that you can solve for x. Very similarly, if you're trying to find the y-intercepts here, you would simply plug in 0 for x and then solve for y. And again, that makes sense. If you want to end up with your y-intercepts, you're going to go ahead and set yourself up to solve for y in that equation. So here in the next example, it says find the intercepts of the graph of the equation 5x minus 4y is equal to 12 algebraically. What we would want to do is plug in 0 for x and solve for y, and then vice versa. Plug in 0 for y and then solve for x, and that would give us our intercepts here. Okay, so let's go ahead and do that, right? So let's go ahead and plug in 0 for x right here, and then we'll solve for y. That'll give us our y-intercepts, and then separately we'll go ahead and write another copy of the equation, but this time we'll go ahead and substitute in 0 for y and then see what that ends up with, right? So 0 here, 0 there. Okay, well what happens here, of course, is that when we plug in 0, these terms are just going to straight up disappear for us. So the 5 times 0 is just going to turn into 0 and disappear for us, and then the negative 4 times 0 over here in this equation is going to disappear for us there. And so really the only step that we have to employ here is dividing on both sides. And so we will go ahead and do that in both equations separately, and we are going to end up here with y is equal to -3 and x is equal to a fraction 12 over 5. Okay? Keep in mind that these are the intercepts of the equation, and so for the y-intercept, that's going to be a point with coordinates 0, -3, and for the x-intercept, that's going to be a point with coordinates 12 over 5, 0. Okay, so linear equations will only ever have one x-intercept and one y-intercept, so being able to find both of those pretty darn important, and you can see how easy the process is. You just set one of them equal to 0, solve for the other. So here we have some more examples where we need to find the x and y intercepts respectively. And so here, let's go ahead and plug in 0 for y and solve for x. All right, and then separately we'll do that same thing, plugging in 0 for x and then solving for y. Okay, so 0 plus 0 minus 2. Okay, so plugging in 0 for certain variables and solving for the other here. The easier one to do, of course, is going to be the one that I wrote there on the right, because remember that if you plug in 0, both of these terms are going to fall away, just leaving you with a -2. And so y is equal to -2 is what we're going to have there in that, that equation that's there on the right. Okay, so y is equal to -2. And of course, that corresponds to a point with coordinates 0, -2, and that's going to be our y-intercept there on that function. For this other one, that is more of a quadratic, and so we are going to need to go ahead and solve that quadratic equation. Lots of different ways to solve a quadratic. You can complete the square. You can do quadratic formula. Here I'm just going to go ahead and simply factor. Factoring should have been something you guys did in your previous algebra class here, so I'm not going to dwell too much on this process. We'll just go ahead and say here that this is going to be a +2 and a -1, and then set both of these individually equal to 0 and solve. We would get x is equal to 1 and x is equal to -2. And those are going to be our two x-intercepts, so those, of course, correspond to points with coordinates 1, 0 and -2, 0. And these would be our two x-intercepts here for this function. Okay, so there we go. So two x-intercepts and one y-intercept in this problem. Okay, moving on to the next one, we have a little bit more of a rational function. Again, we're going to do the same process. We're going to go ahead and plug in 0 for y and then solve for x. And then we're going to go ahead and do that reverse of that process to get our other intercept there. So y is going to be equal to x plus 1 all over 4, and then we're going to have y is equal to 0 plus 1 all over 4. Or sorry, not over 4, but under 4, I should say. There we go. So 0 here, 0 there. And then we're going to solve these for their respective variables. So what happens in this one on the right is 0 plus 1 on the bottom is just going to turn out to be 1. So we're going to have 4 over 1. Or in other words, it's just going to simply be 4. And that's going to be our y-intercept here in this problem. So that's going to correspond to a point with coordinates 0, 4. For our y-intercept. For the next one, we just need to go ahead and solve that equation. 0 is equal to 4 over x. And the thing about this is that there's really no value for x that's going to turn that entire expression on the right-hand side into a value of 0. And so it turns out here that this is actually an equation with no solution. And so what that is going to translate to for us in terms of intercepts is that you do not have a y-intercept in this problem. This is going to be an example of a graph that does not touch the y-axis whatsoever. Okay, so we're going to box that as our result for the x-intercept, or sorry, the y-intercept, and then box this as the result for our x-intercept. Okay, moving right along. There are a lot of slides in this set of notes, so we just want to kind of go quick. This is more of an ACT prep type of question. It says solve this equation. A times x plus 3 is equal to 4 minus 2 times the quantity x minus 2. We want to solve that for x. And the only thing that really makes this more challenging is because we have a second variable here in the problem, and that value of a, right? But in terms of the steps, we're going to go ahead and do the exact same things that we've been talking about earlier in this video here. We're going to go ahead and take this value of -2 and distribute it to both terms of that expression here and just kind of show our work as we go through, right? So 4 minus 2x, and then remember a negative times a negative makes a positive. It's going to be a +4 there, and then we're left with the same thing on the left-hand side since we didn't really do anything with it. Combine some like terms on the right-hand side. We're going to have 8 minus 2x is equal to ax plus 3. And then what we might do is combine some of our variable terms, right? So we might go ahead and add the 2x to both sides here. And the way we might write that is just simply ax plus 2x plus 3 is equal to 8. And then bring that 3 over. Okay, and so at that point we would have ax plus 2x is equal to 5. Okay? Now, the next step of this work here would be to note that you are adding two things on the left-hand side, and they both have a common factor in between them. Okay? So this plus this, they both have this factor of x in the mix, and so what that means is we can go ahead and factor that out front. Okay? So x times the quantity a plus 2 is equal to 5, and if our goal is to solve this for x, we're just going to simply take both sides of this equation and divide by whatever we're multiplying times x. Here that is the binomial a plus 2. And what we end up with here is x is equal to, we'll write this over to the side, x is equal to 5 over a plus 2. Okay? And that could be for any value of a that we want except for a single value of a, and that here is going to be a value of -2. Okay? And the reason for that, again, is because it would be the value that would make our denominator equal to 0, and so we'll go ahead and box that as our final result here. So just because our equation contains another variable doesn't mean that we cannot solve for one of the variables. Okay? It'll just mean that our final result will end up being x is equal to some sort of expression that we might have to go ahead and be clear and put a restriction on, so we can't divide by 0. Next example here, geometry application. It says the surface area, S, of the rectangular solid in the figure is given by that equation involving S and the variable x. Okay? It says find the length x of the box if the surface area is 248 square centimeters. Okay? Well, what we're going to do simply is take out the s, and we are going to go ahead and put in its place what s is equal to. So that would be 248. So 248 is equal to that big equation there. So 2 times 24 plus 2 times 4x plus 2 times 6x. And that would just be a linear equation that you would want to go ahead and solve in the usual way. For the sake of time in the video, I'm not going to go ahead and demonstrate all of the steps for that. I'll just go ahead and use my computer algebra system I've got here in my hands to go ahead and get the solution for us so that we can go ahead and move on. So let me go ahead and just do that here really quickly. Solve this for x. What you should find at the very end of this process is that x is going to be equal to 10. And so if you interpret that in terms of the actual context of the picture, remember that was a length right here, and so we might just go ahead and say that the length there would be 10 centimeters. Okay, so solving that linear equation would result in that value of x. Again, that would just be a straightforward solving process, and you would get that same value here. Last example for this video, example 10, thank you for bearing with me, a word problem. Okay, so it says the number y, and that is in millions, of female participants in high school athletic programs in the U.S. from 2000 to 2010 can be approximated by the model y is equal to 0.045 t plus 2.70, where t is a value that ranges from 0 to 10, and we have an interpretation for t. So this is not something that we can forget. When t is equal to 0, we interpret that as that being the year 2000. What they want us to do here in part A is find algebraically and interpret the y-intercept of the graph shown. Okay, so that's this graph down here. So the y-intercept, of course, would be where we cross the y-axis, and that would be right there, of course. Okay, and so we would just need to go ahead and interpret that and then also find it algebraically. So let's go ahead and find it algebraically first, and then we can go ahead and interpret that result. So to find the y-intercept, we want to set ourselves up so that we solve for y. So that means we're going to take our equation, which was y is equal to 0.045 times our t, and then plus 2.70. Okay? Well, if I'm trying to find my y-intercept, and that means I'm plugging in 0 for x, and I'm solving for y. Well, remember that when we plug in 0 there, this whole first term is going to disappear from the problem because 0 times 0.045 is just going to be 0, and we're just going to be left here with y is equal to 2.70. Okay? And so what we need to do, now that we know what that is we need to now interpret that in the context of this problem. Okay? So what is that going to mean? Well, keep in mind that a value of t being 0 corresponds to the year 2000. So we might interpret that as saying in the year 2000, y was equal to 2.70. And just don't forget what y represents. It represents the number in millions of female participants in high school athletic programs that year. So what that's going to mean is we're going to have 2.7 million females participating in athletic programs that year. And so a really quick and easy interpretation just like that would be good enough for me, okay? And in part B, it says, use the model to predict the year in which there will be 3.78 million female participants, okay? Well, keep in mind, Y is that value that represents the number of female participants. So what we might do is simply just go ahead and take our model, which again is Y equals 0.045t plus 2.70, and because Y is the variable that represents the millions of females, what I might do is take this model, erase Y, and replace it with that value 3.78. Okay, and that gives us a really quick equation that we can go ahead and solve here. And yes, it deals with decimal numbers, but it does not mean that any of our usual problem-solving steps will change. It just might mean that we need a calculator for certain steps. So if we go ahead and do that, then we are going to end up with 1.08, and that is equal to 0.045t. And of course, the last step of this would be to go ahead and divide both sides by 0.045, and we would get our final result by plugging that into the calculator. Okay, so t here is going to be equal to, let me just do this in my calculator I've got in my hands real fast. We are going to get 24 right on the dot. Okay, and now let's go ahead and interpret that in the context of the problem, right? If t is equal to 24, what does that mean? Well, t being equal to 0 represented the year 2000. And so if t represents 24, then that means 24 years after 2000, or in other words, 2024. Okay? So I might just go ahead and box both of these. One is our actual answer, the other is the interpretation of that answer, and that will complete the problem. Okay, so it's my hope that this video has been of some help to you. I know it was a long one, so thank you for bearing with me. Solving linear equations in one variable. Very, very simple, but I hope that I've given you guys some strategies in this one to help you find some success with some more complicated linear types of equations. So if you guys have any questions, feel free to let me know, but that's all I got for this one. Thank you very much for your attention, and I will speak to you in the next one.